Okay, the question is, how do we determine whether something is a good leaving group, a good nucleophile, and then a quick review of basicity. So let's start with the idea of a quick review of basicity. So if I have a periodic table that has CNOF, and then there's a sulfur here, there's a chlorine, a bromine, an iodine. So the main group of the periodic table. In terms of basicity, looking at the periodic table, an OH minus is a stronger base than an F minus. And if you remember from general chemistry, the reason for this is because basically OH minus will completely deprotonate. Like for instance, an OH minus reacting with water will deprotonate that to form H2O, and even though it forms another OH minus, it still deprotonates. This is a 100% complete reaction, whereas F minus, when we take F minus and we react it with water, there's an equilibrium between HF being formed and OH minus. So OH minus is a much stronger base than is F minus, because F minus only really partially reacts with water, and OH minus completely reacts with water. Now we can look at this from the acid standpoint. So for instance, is HCl a strong or a weak acid? What's the definition of a strong acid? A strong acid is one that completely dissociates in water. So that means when I take HCl and I add water to it, I end up with the hydronium ion and Cl minus. So HCl is a strong acid. What about its conjugate base, Cl minus? Well, is Cl minus even a base? If I took Cl minus and I placed it into water, would I form any HCl or hydroxide? And the answer is not. No, I wouldn't. So what I like to say is that HCl is a strong acid because it completely dissociates. The conjugate base of a strong acid is a non-base because Cl minus doesn't act as a base. And what does it mean to be a weak acid? So in general chemistry, you probably did a lot of problems with either acetic acid or HF, and you know that when you reacted those with water, you can go back and review, they were always in equilibrium with their conjugate bases and hydronium ion. And so these are examples of the weak bases. Why are they weak bases? Because they only partially dissociate. And if they only partially dissociate in water, then that means that they're conjugate, let me go back, weak acids. So these are weak acids because they only partially dissociate, which means that there's an equilibrium involved, and their conjugate bases are also going to be weak because they're going to be involved in an equilibrium when you react them with water. So for instance, as I just showed you, if you took F minus over here and you reacted it with water, you would get an equilibrium forming HF and hydroxide. So in my acid-base world, which is probably unique, but it's a little more descriptive. Strong acids have non-bases as their conjugates, and weak acids have weak conjugate bases. So the opposite of strong is non, and the opposite of weak is weak. It goes against the English language, but it really describes what's going on. So strong, completely dissociating, weak, equilibrium. And the conjugate bases then, if something completely dissociates, its conjugate base isn't going to react as a base. On the other hand, if your weak acid dissociates, then your conjugate base is going to react also in equilibrium, so it's going to be weak. Okay, and so that's how we're going to judge the acid base. That's how we judge acid base strength. There's one other issue that I would introduce, and that's the idea that if you dissociate HA into H plus and A minus, there are ways to push the equilibrium towards the formation of more H plus and A minus, and if you do that, you are going to make a stronger acid. So how can I push this equilibrium towards the formation of more products? You might say le Chatelier, right, which in French means the Chatelier. But Le Chatelier's principle only works if you increase the concentration of one of two reactants, or you remove one of the products as it's formed. So Le Chatelier's principle doesn't work here. Because if you increase the concentration of HA, yes, you'll make more HA, but you'll also make more A minus, and so you don't make a higher percentage of H plus. So you can't use Le Chatelier's principle to push the equilibrium. Now what we can do is we can make A minus more stable. And if we make A minus more stable, then the issue becomes, okay, how do you do that? And if you do make A minus more stable, what will happen? It will really push the equilibrium to the right. You'll get more A minus formed. You'll get more dissociation of HA, and you'll get more H plus. If you get more H plus from HA, what does that make HA? Stronger. So one of the classic ways that we can make the acid stronger is to make the conjugate base more stable. And one of the easiest ways to do that is resonance. So let's take a look at that. So for instance, we know that H2SO4 will dissociate into H plus and HSO4 minus. Why is HA, and this is a complete dissociation. Why is it a complete dissociation? Well, let's look at the structure of HSO4 minus. HSO4 minus is going to look like this. That's the structure of HSO4 minus. HSO4 minus is pretty stable. Why? Resonance. I could take this pair of electrons, go here, and draw a second resonance structure that looks like that. And then we would have my O minus up here, double bond O, double bond O. Or I could take this pair of electrons, move it back down here, and draw a third resonance structure that looks like this. So this HSO4 minus conjugate base is going to be very stable. Why? Because it has lots of resonance structures, And if we go back to the beginning of organic, in our review of general chemistry, what we said was the more resonance structures you can draw, the more stable the molecule. So the way that we can push the equilibrium towards the formation of more H plus, but also more conjugate base, is make that conjugate base more stable. And a classic way of doing that is by introducing the idea of resonance stabilizing the conjugate base. Okay. So those are the basic reviews that we need for looking at acids and bases. I have one more piece that we need to talk about, and that is, in the periodic table, how does acidity and basicity go? Well, it turns out that what is a stronger base? A C minus, an N minus, an O minus, or an F minus? Well, down here I introduced the idea that hydroxide is stronger than fluoride. If I continue that, that means N minus is stronger than N minus is stronger than O minus and F minus, and C minus is the strongest of them all. So as we move on the periodic table from left to right, sorry, right to left, basicity is going to increase. Okay. Now down here, let me write my CNO, F, Cl, Br, and I. What does it mean when I go from right to left? No, I quit. When I go from left to right. When I go from left to right, what happens to acidity? The acidity increases. So what's the strongest acid in this sequence? HF. HF is stronger than water, stronger than ammonia, NH3, stronger than methane, CH4. So as you go across the periodic table or in a horizontal direction, going from left to right, acidity increases. Going from right to left, basicity increases. Okay? So we need to remember that horizontal relationship of the elements on the periodic table. Now, what about the vertical ones? Well, HF, as we've already seen, let's just look at the acid strength first. HF, as we have already seen, is a weak acid. Why? Because the HF is in equilibrium. It only partially dissociates in water, and so therefore the HF is a weak acid. What about HCl? HCl, we know we classify as a strong acid because it completely dissociates. HBr is an acid that completely dissociates. HI is an acid that completely dissociates. Going down the periodic table, acidity increases. Now you might say, if HCl, HBr, HI, if they all completely dissociate, how's HI a stronger acid than HCl? Well, here's the problem with that. The problem with that is the idea that HCl, HBr, and HI 100.00% dissociates is one of those little white lies we tell you in general chemistry. They actually don't completely dissociate. It's a big equilibrium constant, but they don't completely dissociate. And so if you took into account the fact that HCl 99 point something % dissociates, An HBr 99 point higher number dissociates. It turns out that HBr slightly dissociates more, HI dissociates the most. It's not 100%, but it's pretty close. And so when we say it completely dissociates, it doesn't. HI dissociates more than HBr and more than HCl. But the little white lie in general chemistry is it's not 100.00%. So as you go down the periodic table, the acidity increases. HF, then HCl, HBr, and HI. So HI is the stronger acid. HF is the weaker acid. Let's reverse that now and look at their conjugate bases. Remember, the stronger an acid, the weaker its conjugate base. There's always that inverse relationship. So if I look at I minus, Br minus, F minus, and Cl minus, as you go up the periodic table, the basicity increases. Now again, I minus, Br minus, and Cl minus don't react with water to any appreciable extent, and F minus does. So as we go up the periodic table, then we would say that the basicity increases. Again, we're looking at very small differences between Cl, Br, and I. As I go down the periodic table, then I would say that basicity decreases. Okay, so this is how we use the periodic table then to determine acidity and basicity relationships. And some of this is just observational, that's what we find. Others, there's a theoretical relationship, but I'm just going to get into this is what we find. Okay, so to review that, going across the periodic table in a horizontal direction increases acidity, and then if you want to increase basicity, you go in the opposite direction. Going down the periodic table, acidity increases. Going down the periodic table for basicity, it decreases. So again, it's always opposite relationships. So that is a not so quick review of basicity and acidity trends and what is a strong acid, strong base versus a weak acid, weak base. Okay, now we need this in order to answer the ultimate question here is, what makes a strong nucleophile? What makes a strong leaving group? What makes a weak leaving group? What makes a weak nucleophile? And they have two different sets of rules. I'm looking at this reaction. I'm taking my nucleophile. I am reacting it with a carbon that has a leaving group on it. We will start this leaving group being a halogen, fluoride, chloride, bromide, iodide. The nucleophile comes in, kicks off the leaving group, does an Sn2 reaction, and then that nucleophile is attached to the carbon, and we end up with the leaving group being kicked off. In this case, again, forming a halide ion. So this is our Sn2 reaction. And so let's talk about strong and weak nucleophiles and strong and weak leaving groups in that context. Okay, let's start with leaving groups, because leaving groups are easy. The strength of a leaving group is inversely proportional to its base strength. So the strength of a leaving group is inversely proportional to its base strength. That means that the stronger the base, the poorer the leaving group. Okay? And that's it. It's an inverse relationship between base strength and leaving group ability. So using our periodic table relationships that I just showed you, if I said F minus versus I minus, which one of these two would be the best or the better, which one of these would be a better leaving group, you would say, okay, got your answer? You would say I minus is the better leaving group because it is the poorer or weaker base. F minus is going to be a poorer leaving group because F minus is a stronger base. Okay. Now, I'm only going to talk about the halogens for the moment in terms of leaving group ability. So if I wanted to create the whole table, I would say F minus, well, I would reverse it. I would say this. I minus is a better leaving group than Br minus, which is a better leaving group than C minus, which is better leaving group than F minus. So here is the better leaving group, and here is the worse leaving group. Okay. Now let me come back to this in a minute or two, or 5 or 10, and talk about, you know, another type of leaving group that actually would be better than a halogen. But now let's move to strong nucleophiles, nucleophile strength, or what's called nucleophilicity. So in nucleophilicity, there are a series of rules that we want to follow. Number one, in the nucleophilicity world, a negative charged nucleophile is stronger than a neutral nucleophile. Now this begs the question, what is a nucleophile? And a nucleophile is something that is electron rich. It's something that has lone pairs to donate. So if I take for my I minus has lone pairs to donate because it has 4 lone pairs. The I minus then can donate the lone pairs and act as a nucleophile. So this would be true of any of the halogens because all the halogens have 8 valence electrons, 4 lone pairs. That gives them a negative charge. And so any of them can donate to as a nucleophile. What are neutral nucleophiles? And there are other charged nucleophiles. For instance, there is a C triple bond N minus would be cyanide ion. There is, well, hydroxide would be a good one, would be a strong nucleophile. So the idea here is that anything that's charged is going to be automatically defined as a strong nucleophile in our world. And we have to start somewhere. So negatively charged nucleophiles will be strong nucleophiles. Neutral nucleophiles we will consider to be weak. So what are some examples of molecules that have lone pairs that they can donate, but they're neutral? Well, that's easy enough. Water. Oxygen has lone pairs. It could be a nucleophile, but it's neutral. Change the hydrogen and make it an alcohol. An alcohol can be a nucleophile, but it's going to be weak. Okay. And those are going to be the two we start with. So neutral nucleophiles like water and alcohol are going to be weak nucleophiles, and negatively charged nucleophiles are going to be strong. Okay, so that's our first starting point. Then, if I'm going to look at the negatively charged nucleophiles, and I'm going to compare one to the other, I have to look at what the relationship is on the periodic table. So now I'm just going to deal with charged nucleophiles, and what I'm going to say is this. I'm going to deal first of all with those that have the horizontal relationship. Let's go with something like a C minus, an N minus, an O minus, and an F minus. So for instance, I could take hydroxide versus fluoride. Who is the stronger nucleophile? Well, when you're comparing atoms, or when you're comparing nucleophiles that have a horizontal relationship, that is only based, the nucleophilicity is based on base strength. So, in this case, the O minus and versus F, which one is the stronger base? Okay, you've got to rewind the video, and you have to go back and say, okay, when I have this periodic table, as I'm going from right to left, what's happening to basicity? Basicity is increasing. So who is the stronger base here? OH minus. So OH minus being the stronger base will be the stronger nucleophile. Okay? So whenever you're looking at horizontal relationships, it is always the stronger base is the strongest nucleophile, or stronger nucleophile. Okay? So that's for horizontal relationships. So who's the strongest nucleophile in this whole series? The strongest nucleophile is a C minus. Now, we're going to have some difficulties here in the future, because what we're going to find is that, remember, a strong base is also a strong nucleophile and vice versa. So in the future, when we get to using strong nucleophiles that are also strong bases, we're going to have to talk about their sort of split personalities. What are they going to do first? They're going to act as a nucleophile, or are they going to act as a base? And we'll come to that. Horizontal relationship, direct relationship, stronger nucleophile is a stronger base. Of course, what happens in a vertical relationship? In a vertical relationship, we have an F minus, a Cl minus, a Br minus, and an I minus. Okay, now this is totally based on experimental results. When you do an experiment and you try and figure out who is the strongest nucleophile, what you find is that I minus is the strongest nucleophile, and F minus is the weakest nucleophile. And you can say there, okay, in a vertical relationship, it's going to be inversely related to base strength. Right? Because the strongest nucleophile is F minus, but yet it's the weakest nucleophile. Now, let's look at this, use a slightly different term to look at this. Because it turns out basicity isn't really what's going on here. What's going on here is what is called polarizability. It turns out that as you go down the periodic table, polarizability increases. Now, what is polarizability? I have always defined polarizability as squishiness. That is how I've always defined polarizability. All right, what is squishiness? Squishiness is the difference between a golf ball and a Nerf, I'm sure it's trademarked, a Nerf ball. One is not squishy and the other one is. Okay, and you might say, well, that's pretty absurd. Not really. Because when we talk about squishiness in terms of polarizability, what we're talking about are the electron clouds. How deformable are the electron clouds? And so when you go down the periodic table, what happens to your principal quantum number? You go from 1 to 2 to 3 to 4 to 5, etc. What are those principal quantum numbers, or the row numbers, or in the really old literature, shell numbers? What do those mean? Well, those are correlated to how far the valence electrons are from the nucleus. And so remember that the farther away the electrons get from the nucleus, the less tightly they're held because of shielding effects of the electrons that are in between them and the distance, etc. So the valence electrons are farther away from the nucleus as we go down the periodic table. If they are farther away, they are held less tightly, and we can deform those electron clouds, hence squishiness. So iodine, being a bigger ion, its electron clouds can be more deformed than a fluorine, and so I sort of treat iodine as if it's a Nerf ball that I can squeeze and I can deform the electron clouds, and fluorine is more of a very solid golf ball that I can't deform because those electrons are held very tightly to the nucleus. So what we find is that as you go down the periodic table, polarizability increases. Basically now the more polarizable, the stronger the nucleophile. And so as you go down the periodic table, if you go down the periodic table in a vertical relationship, your nucleophile gets stronger. So I- is a stronger nucleophile than F-, which is going to lead to a paradox here that I need to come back to. There's multiple things I need to go back to. Now, if you're sitting there going, well, great, okay, squishy, polarizable, but what does it have to do with Sn2 reactions? Well, here's what it has to do with Sn2 reactions. My nucleophile is going to bring its pair of electrons into the carbon and form the bond between the carbon and the leaving group. So this pair of electrons is going to come in, it's going to add to this carbon and kick off the leaving group. Let's draw the orbital picture for that. And so the orbital picture is going to look like this, where here's my leaving group, and so the leaving group orbitals are going to overlap, and then of course we have my hydrogens here. And this is always going to be an sp3 hybridized carbon. And what does that mean in terms of the nucleophile electrons coming in and now basically forming a bond with the carbon? Well, whenever we form a bond, we are overlapping orbitals. So now it is time we invoke the sp3 tiny orbital that we haven't invoked since we talked about hybridization. What do I mean? Remember that an sp3 hybridized carbon has a big lobe, and it's got the little teeny tiny lobe down there. That little teeny tiny lobe comes into play here, because for this orbital, there's a little teeny tiny lobe on that side. And so what happens is when the nucleophile comes in, it actually overlaps its orbital with the lone pairs with that little teeny tiny lobe, and then it forms the sigma bond that way. Okay, and that's the backside attack in an Sn2 reaction. That's going to be how the nucleophile attacks from the backside. Well, the more electron density that I can put into that lobe of the nucleophile, and the higher the electron density, so the more electrons I can put per volume, is going to help form a stronger bond here as the nucleophile comes in and attacks that carbon from the backside. What that means in terms of the energy diagram is that the more electron density I can put into this lobe, the lower the activation energy, or the lower the transition state energy. I'm going to get a lower transition state, and I'm going to have a lower activation energy. And what's that going to do? That's going to make the reaction go faster. And so by being able to concentrate electron density into that lobe, the nucleophile then will react faster in an Sn2 reaction. And so that's where the squishiness, the polarizability comes into play. If you are an iodide, you are large and squishy so that you can deform your clouds and put more electron density into a smaller volume by deforming. Sort of like constrict a Nerf ball. But if you are an F minus, you're fixed. You can't increase the amount of electron density within that lobe because you're like a golf ball. There's nothing to squish. So this is the explanation that we use to say this is why I minus is a stronger nucleophile and F minus is weaker because I minus is more polarizable than F minus is. So as we go down the periodic table, the valence electrons are held less tightly. That leads to this polarizability squishiness of being able to put more electron density into an orbital that will then overlap better with the little teeny tiny sp3 orbital in an Sn2 reaction. That's going to cause that transition state to have a lower energy, which means overall the reaction is going to have a lower activation energy, which means it's going to occur faster. And so that's our whole reasoning behind that. Okay, it's a lot to digest, but you can go back and play the tape again. So this leads to kind of the paradox. So of F, Cl, Br, and I, who was the best leaving group? Iodine. Why? It's the weakest base. Who is the best nucleophile? Iodine. Why? Polarizability, squishiness. So what does that mean? That means if you want to do a substitution reaction, don't use iodine. Because if you think about taking something like a chloride and reacting it with a carbon with an iodide on it, the chlorine's going to come in and kick off the iodide. And that's going to work great because iodide is a great leaving group. But then what's going to happen on the other side? The iodine is a good nucleophile, so it may come back in and kick the chlorine off, which means if you do reactions with iodine, you might end up with some equilibrium. So when we want to do substitution without that equilibrium, we shouldn't use iodine, because it is both the best nucleophile of the halogens, it is also the best leaving group of the halogens. Right? So that is what makes a strong nucleophile. Okay? So just a quick review. Negative charge nucleophile stronger than neutral. We classify the negatively charged based on their relationship on the periodic table. If it's horizontal, then stronger base, stronger nucleophile. Vertical, more polarizable, stronger nucleophile. Do I want to go here? Sure. I will go here, because I'm sure somebody, if anybody's watching this, would say, yeah, what about the sort of a diagonal relationship? How's that going to work? Okay. Here's how we're going to classify things. We're going to say that the C minus, N minus, O minus, S minus, that these are always going to be stronger nucleophiles than, they're going to be stronger nucleophiles than any of the halogens. So if I have an OH minus, the OH minus is greater than any halogen as a nucleophile. Okay? Just as simple as that. So that kind of that'll take care of some of the diagonal relationships. Of course, if diagonal relationships go in the same direction, meaning down, and to the left, then you can end up with them going in the same direction. It's when a diagonal relationship goes in opposite direction who wins, basicity or polarizability. And in general, I would say the basicity is more important than polarizability in terms of a horizontal versus a vertical relationship. And that's what you have here. You have the horizontal relationship of these four being more important than the halogens. Okay, so that's, again, not a short answer, but that is how we classify strong and weak nucleophiles and strong and weak leaving groups. Except I want to go back to the leaving groups and finish it up, and yes, I'm finishing it up with one last issue. And that issue is going to go back to the idea of resonance. So in problem 7.15, I recorded a video for that that you can find on the YouTube page or through Piazza. My best leaving group is I minus. The only thing that is going to be better than I minus is to find a weaker base. Well, if we go back here and we say, remember this fundamental relationship that if I can make the conjugate base more stable, I can make it weaker because the conjugate acid becomes stronger, then what I can begin to do is to put together a leaving group that is stabilized by resonance. And here's how I do that, and this is what's in problem 7.15. If you have a carbon that is attached to an oxygen that is then attached to an S double bond O with an R group. And that R group will be different things, and we'll talk about that in the future. But if I could create that as my leaving group, then my nucleophile will come in attack that carbon and kick this thing off. And when it does, it's going to form an O- attached to an S double bond O, with an alkyl group on the other side. Is this a weak base? Absolutely. Why? Because it's stable. Why? Because it's stabilized by resonance. So in general, our best leaving group would be I-, but if I can actually create this as a leaving group, it will be even better. So I'm kind of combining now what I started with, the idea of forming a weaker conjugate base by stabilizing it by resonance. That works to the advantage of making a really, really, really good leaving group that is actually better than any of the halogens. Okay? So that's kind of where we end up here in our strong versus weak nucleophile. It is not a simple question, and I've given you some review on acids and base strength and how to determine those.